Hello guys, Free here. Welcome to our demo for today. It's going to be a really exciting demo, and we're going to be looking at quantum computing. And specifically, we're going to be looking at D-Wave. It's a company that has an implementation of quantum computing, which is really powerful, really exciting, and basically where the future is going. I have to admit, this is going to be one of those demos that gets a little bit over my head, and hopefully I'm going to look back at this demo to say, hey, I was kind of shallow in my thinking, and hopefully learn a lot more as we go through this process. So this is going to be more of a learning and a discovery process more so than a demo process, just because, if I was to quote Richard Feynman, where we're going to be talking about quantum computing here, he says, no, if you think you understand quantum mechanics, he was talking about that specifically, you don't, right? And it's true for quantum mechanics, and I think it's probably true for quantum computing. So that said, the system we're going to look at is D-Wave Leap. So D-Wave is one of many companies that are implementing solutions around quantum computing. We know the classical computer has been around for a while. I hate to even imagine that talking about computers, we're talking about classical computer, just given how transformational it's been for civilization. And we're already talking about classical computer like it's we're talking about classical Roman history or something, right? That just tells you how fast innovation is happening. But that said, the classical computer has been around. It's been very powerful. It's led to the revolution that we've seen and the growth of human knowledge and potential all the way to the internet and transform our lives in unthinkable ways. And now we have this next generation computers, which is going to be basically, if it comes to fruition, that would be the quantum computers. So a couple of things before we dive in, so you can see on my screen here, D-Wave Systems. You can go on your website. They have the Leap, which is one of their projects or products, I would say. And basically, behind the scenes, we have access to a quantum computer that you can access to solve your problems. Now, again, like I said, I'm not fully sure I understand what's going on here, but it definitely seems promising. And as a futurist at heart, I'm going to keep a very close eye on this and learn as much as I can as this technology evolves. So, just a couple of things to be aware of. Classical computers, we talk about CPUs and GPUs. With quantum computing, we talk about QPUs, right, which is a quantum processing unit, which is going to be interesting. So once you log in here, which I did here at Tech with Fro, you can see some demos. So they have a Leap, which is kind of their workbench for quantum computing to access the quantum computing servers they have. You can interact with the demos that they have, and some of the demos are around social networks, which is a very common use case for problem solving, and factoring, which is another case. So the use case for this is not necessarily to replace, and this is where people get a little bit tripped up or confused here, is quantum computing going to replace classical computers? And I don't think that's the case. Anyone smart in this field or knowledgeable here will tell you it's not, the goal is not to replace classical computers, but there are certain problem spaces where having a quantum computing might be more efficient than using classical computers, especially ones where you have to scan a very big problem space to find specific results. Like social network is one, factoring is one, factorization of prime could be another one, which could really throw a wrench into security. So very, very interesting. Don't be scared. This is not going to replace our classical computers, but it has its place to play. So when we come in here, let's go up. A couple of things that we're going to do is there is this Ide Workspace that you can click, and it brings you in here. You can open that up. And I think what they have here is almost like a Jupyter notebook or like an IDE that you can use to write programs. And then these programs would, run on the quantum computing behind. And so you might ask, well, why are we writing a program in English, well, or in a programming language? And this is my README. This particular program is going to solve for a Sudoku. You give it a Sudoku, and it's going to solve to say, is that correct or is it not correct? And this is the requirements text. And it has requirements in here. The problem is here. All right, so I'm not going to mess around with this problem. Let's just keep it as such. And then we're going to go to sudoku.py. It's been written in Python, but what it does is it takes, just like the way you have a compiler that takes from, you write in one language and it compiles it to something that the machine can understand for a CPU to run. We can write it in Python, but it's going to compile that into something that a QPU can run. So there's a lot of things that are going on here. I still fully don't understand every single one of them, but just to kind of make an attempt at showing how ignorant I am with this, it basically, you get your labels, you get the metrics, which is basically, if you think about the Sudoku, it's a metrics. We're trying to check if it's correct, and we're passing our metrics variable, and it's going in there. But where I think the magic is happening is in this build, the BQM. And the BQM is basically a binary quadratic model. I think that's what it's called. And for the quantum computer to solve this, it has to be in this format. This is what it understands, right? And so this code in here, which again, I fully don't understand, I kind of have to spend some more time to really go through line by line. This was just a quick demo. Takes our problem space and translates that into this BQM. And the BQM is what actually solves it. So when you call the quantum computer to solve your Sudoku problem, you're sending it a BQM, which is it's the encoded, the binary quadratic space that has been encoded, which seems to be some wave functions, and it's going to collapse the wave function and give you a result based on probabilities. At least that's how I kind of understand it at this point, or at least how I kind of don't understand it. But that's what's happening here. So if you can take a problem, encode it into a BQM, and then pass that BQM to solve, this is what makes it into the quantum computer, and it's actually solving it here with the Kebero sampler, right? I believe the Kebero sampler is what actually invokes the quantum computer to do the solving. I might be wrong. If somebody really knows this very well, let me know. I see here it does the sampling, and it does a deep copy. So I'm not sure what this deep copy is doing. I wish I could see deep copy operation on arbitrary Python objects. All right, I'm not quite sure what the deep copy is doing. The Kebero sampler, diamond compatible hybrid asynchronous deep composition sampler. All right, so somewhere in here is what is happening, that the quantum computer solves the problem, and then you get your results back, and then you can iterate through the results to make it human readable, right? And you can rebuild your BQM and return, what do we return here? Well, we just print it on the screen. All right, so that's it. I really don't fully understand, but let's try it. Let's run it. I don't understand what the specific function is doing or where the quantum computing comes into play. But assuming we do, and you can encode your problems into a BQM and send it for solving, you have a Sudoku, which is just an n by n or n by m matrix thing. You can submit that, and we're submitting that. It's gonna run through it. Not the fastest. If I'm timing this, it's what, 10 seconds already. Before we get a solution, I would think that the quantum computer should be faster. And that goes into asking, what benefits do we get from a quantum computer if you get the same performance that you get with a classical computer? And that's where, again, the problem spaces, this is kind of a trivial problem to solve, but I'm assuming that there are bigger problems like network and security and drug discovery, route optimization that are better with like a quantum computer than your classical computer in terms of the resources that it takes. So, just because this is a trivial problem doesn't mean that space is not relevant. So in this case, the solution is correct, right? Apparently, we've used a quantum computer, right? Congratulations to us. Tech with Fru, really good. Let's go back into my problem and let's change that to, can I change it to a 9? All right, change that to a 9. And where is save? I don't know where the icons are. I'm assuming that it's going to save. I want to hit on save. Control S. Oh, okay, that saved it. All right, let's go back to my sudoku.py. If I run that, I'm guessing that it should refuse that. It should say not correct. The solution should not be correct because I changed the value. Hopefully. And that's one of the things where with some of this, if the problem is so complicated that no one can reasonably validate the solution, that becomes a problem in itself, right? error. So there's an error. So it's incorrect. But how did it get to this? I can't explain. So just going back to my little rant there, if the problem is so complicated that validating the solution is a problem in itself, are we kind of talking about is P equals NP here? Or is P not equals NP, right? Which is a big problem in mathematics, but maybe not. I don't know enough about what's going on to even say, is this just messing around with me or is it not, right? And this is a trivial problem which we can validate. What about really complex problems where validating the solution might take as much time as solving the problem in itself? Would we ever know if we're getting correct answers or not? Hopefully, you get what I'm getting at here with my P equals NP problem. Maybe I'm missing something here with my limited knowledge, but very interesting. Quick, and this is an Apache license, so I'm impressed with that. A quick demo of it. I did spend some time before the demo, just kind of reading through some of the documentation about, you can see me highlighting the binary quadratic model, trying to understand basically how you take a problem and you formulate that into a BQM. And it goes in here. In a classical computer, you can take a simple statement like, an area equals pi raised square, which we all know, and the computer can understand it like this. But with the BQM for a QPU, which is the quantum processing unit, it encompasses it as almost like a quadratic equation, which you can graph, right? Quadratic equations are basically, you can think about it as graphs as well. Equations and graphs are the same things, just in different representations. And that graph is what gets sent over, or the wave function is what gets sent over to the quantum computer, and it somehow collapses that wave function and then gives you the result from a solution space. All right. Do I really understand all of this? I don't. I really don't, but I'm trying. I'm going to try to make sure I fully understand what's going on here, because I think the promise could be really, really big. All right. So I'm going to keep trying. Then this is what the BQM is. You can see I did a lot of reading a little bit to just understand that there's some vocabulary, a BQM, a chain length, a chimera, a hoof. All right. And this is a whole body of knowledge that I really need to spend some time and dive into a little bit more. But you can use it, just like with classical computers, you can use a computer without understanding how bytes and zeros work, right? No one stops you from using Microsoft Word if you don't understand how data is stored on disk. But if you're gonna make videos about it and be educated about it and go underneath, that's just where I'm trying to take that next step here. And hopefully in the next couple of months or years, my knowledge about this will be clear. So basically BQM, the binary quadratic model class encodes Isings and quadratic unconstrained binary optimization models used for samplers such as D-Wave systems. So that's basically what it is. So Cubo is one other piece, which is a quadratic unconstrained binary optimization. And it's basically a function. And I don't know if it's interruptible with the one that AWS has and the one Azure has their own quantum computing service. I don't know if all of this, once you encode in BQM, if you can run it on the AWS qubit, or if you can run, I believe they call it qubit or something, or Azure has their own, basically they have their own quantum computing. So I don't know if that would work there too as well. But very interesting, very quick. This is something you can get your hands on if you want to see a quick demo of this. Just go over to D-Waves, and they have the system called Leap. If you go to D-Wave, they have Leap. You can explore examples. In here, there are examples around Sudoku, which we saw. Nurse scheduling is another example, which you can see how they use this for scheduling nurses, I guess, in hospitals in a very efficient format. And that's almost like a route, not the route optimization, but it's almost like the traveling salesman's problem, which is a very big problem, and you're trying to find the least path in a graph. That's basically what that would do. And then things like I think they call it the minimum vertex cover is basically what this next scheduling problem would be. So MV, minimum vertex cover, the MVC is basically what it is. You can read about that. It's just it's a graph problem. And then another thing to be aware of is the whole idea of superposition, entanglement, and tunneling is what happens behind the scenes. So let's look at the Python code here, which is, I'm sure at some point it should create a BQM and then submit the BQM. This is the first time I'm looking at the code. It doesn't make a lot of sense to me. Can we control find BQM? There you go. So it's created a BQM and it's submitted the BQM to the sampler. But here it's using a leap hybrid sampler. And I think before we used, what's the difference between the leap hybrid sampler and what sampler did this use? The Kebero sampler. So now what is the difference between the Kebero sampler and the leap hybrid sampler? I have no idea, right? So those are the things that, I clearly have no idea what it is I'm talking about, and it takes a little bit more understanding of this to be relevant. So does each problem have its own sampler, and what is this sampler? How do you encode that? Those are questions that I have. But hopefully this kind of motivates you and spurs you up to go think about playing with this and educate yourself. If this is the future, then the best way to prepare for the future is to be educated about it. And I kind of see this as, think about the old Microsoft, right? When Bill Gates was kind of young and tinkering around with a PC in the 60s or so, and his peers were probably thinking he was a crazy kid. But what he did was he built Microsoft. And today the world has changed. And you could be that Bill Gates of today, thinking around with the quantum computer. And while people have no idea what it is and think you're crazy, you might just be the future Bill Gates, or the future you of the future that everybody looks at because of the amazing things you can build with this. And I really don't fully understand the power of this. And it takes people playing with it to understand the power. There's a lot of documentation and resources here. Ocean Software, I'm not really sure what that is, but they seem to have some really good code and documentation. So check it out, guys. Hopefully this was helpful. Just a quick demonstration in a series of demos, and hopefully this inspires you and urges you on to check out D-Wave. I'm gonna do demos around other quantum computing systems, and we're gonna learn along the way as we go, depending on the areas and the problem spaces we're working with. We'll all learn and learn together. Again, thanks for joining. You have been very awesome. I have been through, and I'll see you in our next demo.